Hello, and in this video, what we're going to be doing is we're going to be looking at antiderivatives and applications of antiderivatives for parametric curves. Okay, so we're going to start with the idea of how we used antiderivatives back in Calculus 1, where we could find the area underneath a curve between two endpoints. Okay, so the antiderivative or the definite integral from a to b of f of x dx provides us with this area. So what we're going to do is fix the camera. And what we can do is we can think about rewriting, uh, so suppose we have a parametric curve, x equals x of t, and y equals y of t, between 2 points t0 and t1. And just for simplicity, we're going to say that right here, this is when t is t naught, and right here, this is when t is t1, and we're going in that direction. So if we want to find the area now of this parametric curve, what we're going to do is we're going to think about this in the following way. We used to think about y as f of x, but now y is no longer, so y is really just y of t, and x is x of t. So y locally at least is going to be f of x of t. So this is locally. Okay, what I mean by locally is it may not be on the entire interval that we care about, but over very small stretches of the curve, it's going to be true. So then we can find the area of the curve in parametric form. We're going to be going from t equals t0 to t equals t1 of, so one way to think about this from before was y dx. So this is going to be y of t times dx dt times dt. Okay, so what's going on here is this is going to be the width of our boxes, and this is going to be the height. We take the height, multiply it by the width, do that over enough of this area, and we end up with the total area. Okay, so now that we have this more or less basic framework, in general, we don't actually find areas using this parametric form. What you actually do in real world is you'll use techniques you learn in Calculus 3. Okay, so let's clear this and let's go on to something that we do actually use. So this is extending our arc length formula to now be in parametric form. Okay, so we have a curve, we can think about like this, going from here to here. Okay, so before, when we thought about y equaling f of x, we could find the arc length. This distance here, L, was the integral from a to b. That's a, this is b, of square root 1 plus dy dx squared dx. Okay, and this came from adding up a bunch of little line segments, the mean value theorem, a bunch of little things like that. Okay, so what we're going to do is the following. We know what dy dx is in terms of parametric form. So now in parametric form, okay, so we're going to say that this is when t equals alpha, and this is t equals beta. So we're going along this direction. Our arc length is now going to be the integral from t equals alpha to t equals beta, square root 1 plus, we'll write it as y prime t over x prime t squared dx dt. Okay, but what we can do is we can simplify this. Okay, so maybe I shouldn't have written this as x prime of t and y prime of t. What I really want to do is write it in this form. So this is dy dt, and this is dx dt. Like this. Okay, so what we can do is we can think about bringing this dx dt that's outside of the square root inside the square root. And when we do that, we're going to square everything. So that means we're going to integrate from alpha to beta of, write it as dx dt squared times 1 plus dy dt over dx dt squared dt. And we can simplify this even further by distributing this dx dt squared, because notice what's going to happen in the second piece is it's going to cancel out. So arc length in parametric form is usually written in the following way. So this is dx dt squared plus dy dt squared dt. Okay, so let's look at a quick little example, and we can see how this works more in general. Okay, so let's use this in a non-trivial example. So let's find the length of the curve. Find the length of the curve, C, defined by x equals cosine t, y equals sine t, and we're going to be on the interval from 0 to 2 pi. Okay, so we've seen this a bunch of times at this point. This is your standard circle of radius 1 centered at the origin. So this should be one loop around the circle. Okay, so we can compute the arc length. So dy dt should be cosine t. Dx dt should be negative sine t. Okay, so our arc length, which is the integral from alpha to beta square root dx dt squared plus dy dt squared dt, in this case, is going to be the integral from 0 to 2 pi of square root negative sine t squared plus cosine t squared dt. So this is the integral from 0 to 2 pi of sine squared t plus cosine squared t dt. But sine squared t plus cosine squared t is 1. Square root of 1 is 1, so this is just the integral dt. So this is t integrated from 0 to 2 pi, which is 2 pi minus 0, which is 2 pi. Okay, and if we were to check this algebraically, this is one revolution around the circle of radius 1. So this is the circumference of a circle, which is 2 pi r, in which case r is 1. And we get precisely 2 pi. Okay, so we'll come back and look at a slightly different example and see what's going on there. So thank you for watching.